dielectric heating. This is the cross-section of the high-frequency wood dryer. You see the tank and the rack inside the tank. The tank and the rack are grounded. The wood is placed on top of the rack, and there is another electrode connected to the high-frequency voltage source. The high-frequency electric field between the electrodes causes the wood to heat up due to dielectric losses in the wood. Our task is to calculate the losses and to calculate the temperature rise. First, I'm going to simulate AC conduction problem. The losses in the dielectric are characterized by the loss tangent value. In QuickField, there is no way to enter the loss tangent value in material properties. Instead, I'm going to specify the apparent value of the electrical conductivity. Here you can see the equation how to calculate it. Then, after the AC conduction problem is simulated, I'm going to pass the losses from AC conduction problem to the transient heat analysis problem and calculate the temperature rise dynamics. Initial temperature of the wood is plus 20 degrees Celsius. Okay, let's start QuickField now. In QuickField, I create new problem. Kiln AC. Next, problem type is AC conduction, frequency is 6.78 megahertz. I'm going to simulate only a single cross section, so the model class is plane parallel. The kiln length is 3 meters, and length we need some millimeters. Finish. You can draw the geometry model here, or you can import the geometry model from the AutoCAD DXF file. In the kiln, the wood is placed between two electrodes, so the simple model might be looking like this. I insert a rectangle with the dimensions of 150 by 100 millimeters. This would be the cross-section of the wood beam. This wood beam lays on the thin conducting sheet with a thickness of 2 millimeters. And on top lays another conducting sheet. Insert. Okay. To the left and to the right there are the same wooden beams, and there is some space between the beams, and this space is naturally filled with the air. So switch to insert mode and draw the line here and draw the line here. To the top, to the bottom, to the left, and to the right, there are the same wooden beams. There is no need to draw all copies in the model. You can use this simple model to calculate losses. First, I need to assign labels to the objects. Switch to Select Objects mode, click the object to select, and type in the label name here. This is wood. For labels, I'm going to explain the geometric object's meaning and provide physical properties. This is air. To select multiple objects at the same time, hold the Ctrl button pressed. This is metal sheet. And this is the metal sheet. The bottom sheet is grounded, so at the sheet surface I specify electric potential. For the edge I assign label grounded. And for the top sheet edge I assign label high voltage, as it is connected to the voltage source. Now let's provide physical properties for these labels. Double click the label name in the tree. Electric permittivity of the air is 1. For the metal, I specify electrical conductivity, which is 5 megasiemens per meter. For the wood, I specify electric permittivity, which is 2, and apparent value of electrical conductivity, which is 74.6 microsiemens per meter. Okay, the bottom electrode is grounded, its electric potential is 0. The high voltage electrode electric potential is 1 kilovolt. Please note that domestic 220 volts is in fact a root mean square value. In QuickField, we should specify the magnitude of the sinusoidal wave, which is times square root of 2 higher. So instead of 1000 volt, I should type in 1000 multiplied by the square root of 2. 1000 is the root mean square value, and this is the magnitude. Okay. Before I can run the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now you can solve the problem. Let's take a look at the results. Here you can see the electric field strength distribution, and you can adjust the field picture and switch on the color map of the active power produced in the wood. You see the color map is distorted. That's because in our model we have materials with very different values of electrical conductivity. We have the wood with electrical conductivity of 1 millionth of the Siemens per meter, and we have the metal with the conductivity of 5 millionths Siemens per meter. There is no electric field inside conductors, and there are no losses inside conductors. And there is no need to include metal in the model. This way we'll tell QuickField that most important part is a wooden beam. So I open the label properties and remove all the data here. Now let's solve the problem again. Again, follow the field picture properties and adjust the field picture. Now you see almost uniform power density distribution in the wood. If we adjust the field picture and add more colors to our picture, 200, you will see that it is uniformly colored. You can use the local values tool, click any point and get the exact value of the active power produced at this point. You will see that it's the same in any point. You can use the contour tool, click to select and calculate the total power produced in the wooden beam. Integral calculator, active power produced in volume. 535 watts per one wooden beam with the length of 300 millimeters and the cross section 150 by 100 millimeters. I know that in real kiln the cross section of all wooden beams is 1 by 1 meter, so we can easily calculate the total power produced in the real kiln. Here we have 150 by 100. Multiply by this power. This is the power, 22 kilowatts, that is required to heat up the stock of wooden beams in the kiln. Now let's calculate the temperature. The kiln limits the wood temperature by 70 degrees Celsius, so I'm interested in simulation of transient heat transfer problem to calculate the temperature rise dynamics. I create new problem. Kiln heat. Next. Problem type is transient heat transfer. Module class is plane parallel. Module length is 3 meters and length units are millimeters. I'm going to link electric and thermal problems to pass the losses distribution automatically from electric to the thermal problem. To be able to do so, both electric and thermal problems should be based on the same geometry model file. So here I click Browse and search for this file, Kiln AC mod, that was used in AC conduction problem. Here it is. Next, I'm going to simulate 4 hours. In seconds, this will be 14,400 seconds with a time step of 10 minutes. And the initial temperature of the wood stock is 20 degrees. Finish. Okay, now the thermal problem is created and it used the same geometry model file. The labels are already assigned, but now I should provide thermal properties for these labels. I do not calculate temperature distribution in the air, so I do not specify any properties for the air. Just click OK. For the metal, I specify thermal conductivity of steel 40. Heat capacity is 420 and the density is 7,800 kilograms per meter cubed. Okay. For the wood, thermal conductivity is 0.6. Heat capacity is 2,300 and the density is 800. I do not specify power losses here as I'm going to automatically transfer power losses from electric to thermal problem. So here I left 0. Now, there is no any specific properties to assign to this label, so I do not enter any data here. Just click OK. You see the 0 mark next to the label name. That means this label doesn't contain any physical properties and this label doesn't affect the results. The same is true for this label. Okay, I have the source of the heat inside the wood, but what about the heat sink? Remember, there is an air here and here, and the beam is cooled by the air. So at this side and at this side, I assign label convection. And for this label, I specify the temperature of the air, 20, and the convection coefficient, which is 5. Okay. The vapor cannot go through the metal sheets, and besides, there are other beams at the top, at the bottom, so I don't specify the convection at the top and at the bottom surfaces. Now let's add the link. So far there is no link. Open the thermal problem properties and here follow to the link step. The link type is generated heat and the problem where the generated heat is calculated is Kiln AC, so I browse for AC problem, electric problem. Here it is, open and add the link. Look here. Now the link is added and we are ready to solve this problem. And got the error message. The linked problem results are out of date. Okay, let's resimulate electric problem. Solve. unresolved label convection. Well, indeed, both thermal and electric problem share the same geometry model file, and we have modified the geometry model. We have assigned label to these edges, and we have provided physical properties for this label in thermal problem. But we have to provide physical properties for this label in electric problem as well. Here you see the label appeared in electric problem, and you see the question mark next to the label name. In fact, there are no specific properties to assign to this label in electric problem. So again, I do not enter any values here, just click OK, and you see the 0 mark next to the label name. This label doesn't play a role in electric problem, it only plays a role in thermal problem. Okay, the electric problem has been modified. Let's simulate it again. And then simulate the thermal problem. Let's take a look at the results. Here you can see the temperature distribution after 4 hours of heating. You can see the intermediate results. Let's adjust the field picture. Initially it was 20 degrees. And you take a look at the time plot in any point. Just click the point, right click, time plot, and this is the temperature dynamics. And when the temperature reaches 70 degrees, the voltage source in the kiln will be automatically switched off to let the wood cool down. This way, you can use QuickField to calculate dielectric loss value and find out the heating process dynamics. If you search for the dielectric heating on our website, you will find the example page. Here you can read about problem setup, browse the solution section, look at the resulting pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.